Alright, so this is the problem E from the Code Forces Contest 1095, which is E almost regular brackets sequence. And you're given 3 seconds as a time limit for this and a memory limit of 256 megabytes. You're also given a bracket sequence S consisting of n opening brackets and closing brackets. And we could go over what a bracket sequence is, but I'm pretty sure you all know what a regular bracket sequence is. It's just it fits, everything matches, and nothing starts before it's supposed to start. So for example, these two are bracket sequences in the fact that they are. You see this is open, and then this is closed, and this opens, and then this closed. For example, this one opens, then closes, closes. However, this one closes before it opens, so it's not allowed. And this one just opens and never closes, so again, it's not allowed. And so you are given a bracket which is SI, and basically you can just choose any bracket SI, and if you choose it, then it means that you change it, so you flip the direction of the bracket. And so your task is basically to try and calculate the number of such positions that you can change the type of the ith bracket, and hence the resulting sequence. And then you want to see, will that become regular? So basically you want to, like it says, you want to count the number of positions I, such that if you change the type of the ith bracket using the method they have given, then the resulting sequence will be a bracket sequence and will become regular. So the input is going to be one integer n, which is 10 to the power of 6, and right away this tells us we cannot use an O(n) squared algorithm. We have to do O n log n or better, and preferably n O(n) because that's not less than 10 to the fifth. And the second line of input, and one more thing, this does have a 3-second time limit, time limit, I guess you would say, but that we'll not count on that. Let's try and figure out an O(n) solution. And so the first line of input contains n, and then the second line of input contains just the string s, which is the opening and the closing brackets. So a relatively simple problem. There aren't any test cases, multiple test cases we have to worry about, which will make us have to solve this even faster. We just have to print out the number of positions, which we can change. So one way that people commonly deal with bracket sequences is you assign the opening bracket, which is the bracket that is shaped, I believe it's this way for the camera, yeah, this way, and then you assign this one to a positive one, and then you assign this one, which is the closing bracket, to a negative one. So as you can see right here, you'd assign that a positive value and this a negative value. And usually they're the same value because they have to be the same value for it to work. So this one will be a positive 1 and this one will be a negative 1. And so the way people determine whether or not it is a proper bracket sequence is 1, if you keep on summing. So for example, you start here in this sequence, you start here, you say 1, 2, then you get 2, then you get 3, then you get 4, then you get 3 because now it's negative 1, then you get 2. If you sum like that and the value never crosses below 0, and at the end the value is 0, then you know it's proper. Basically what that means is, have you closed the same amount of times that you've opened? So have you opened the same amount of times that you've closed? And have you opened before you close? So that's really what that does. And we might think to implement that in a sort of O(n) squared solution. Oops, we might think to implement that in an O(n) squared solution by iteratively going through each possible digit that we can, or rather bracket that we can change, and checking the entire sequence to see, has it been changed, will it be proper? But as we said earlier, an O(n) squared solution is not going to work. Then your second thought might be to try and do something relating to O(n) log n. For example, segment or binary trees, because those ones work well with log n operations. But those won't work either because you still need to calculate that sum, that total sum. So at this point, you're probably stumped. And here's where I'm going to tell you there does exist an O(n) solution. So pause the video now and see if you can find that O(n) solution, because that O(n) solution is a really, really good one. It's a clever one, and it took me a long time to figure it out, but I'm sure you guys can. So pause the video now and see if you guys can figure this out, and when you think you have it, you can come back. So what we're going to do is we're going to keep track. Well, really, you've got to think about this for a minute. we're going to keep track of a prefix array. And this prefix array is doing exactly what we said it would. It's going to store kind of the value. So at each index, it's going to store what's the sum up till then. That's how a prefix array works. So here it would be 1, and then the second index, or in C++, Java, whatever language you're using, the first technically index, but we're just going to call it second index, it would be 2, and the third index it would be 3. Fourth index it would be 4, and the fifth index, now see that there's a closing parentheses, so we've got to subtract 1, so it would actually turn back down to 3, and in the final index it would turn back down to 2. The next thing that we're going to want to do is we're going to want to keep track of the minimum kind of parentheses from the right. So what's the minimum value that we ever hit from the right? Because remember, that minimum value can dip below 0 because we're flipping one. So for example, say this, so we've got 2 here, right? Now here we know that the second index, that's going to be 3, but in what we'll call our suffix array, it's going to stay 2 because the still at that point and everything after it, the minimum is still 2. Now here, the minimum is going to still be 2, still be 2, still be 2. And watch out, there's a 1 there, it's going to change to 1. So our suffix array is going to consist of a 1 followed by a bunch of 2's. And what this is going to represent is it's going to let us know that, hey, if we changed this, then obviously we would subtract a certain amount from the remaining. So if we, for example, changed an open parentheses, or we could say an open bit, I'm going to keep parentheses, an open parentheses to a closed parentheses, then we're actually subtracting 1 to get to 0 and another 1 to get to -1. We're subtracting 2 from whatever follows after that. So we're subtracting 2 from each of the following prefix array. And what that tells us then, what we can get from that is you can say, okay, then the minimum after that is going to be, the minimum value that we have is going to be whatever the minimum value was minus 2. We want the minimum value to be 0, and the reason we want this is we want the last value to be 0, and we don't want any other value to be less than 0. So we want the minimum value to be 0 after we flip that thing. So that's what the minimum value is there for. And we also want the other value, which is our last value, to be 0 after we flip that bit, or that parenthesis. And so the suffix array is going to store the minimum value, so we can check, is this minimum value, when it's flipped, going to give us anything that's less than 0. As long as it's not going to give us anything that's less than 0, we're good on that end. Then what we have to do is check the last index of the prefix array to make sure that when we do our operation, either adding to or subtracting to, we hit back to 0. And once we know that both of these two are 0, we know that the minimum value overall is 0, so it never hits -1. And I'll explain why that's important in a second. And our final one is 0. And that one should make a little bit more obvious sense to you. Yeah, hey, it's got to be 0 because we need to end the same amount that we started. So as I explained earlier, we don't want it to be negative, because if it ever hits a negative value, then we know that at some point we have closed too many than we have started. And there's really no way to fix that. There's no way we can add an extra open one at the end, because that's not going to fix that we've closed extra. So we never want it to dip below -1, below 0. So let's actually see how we would implement this into VS Code. I'm going to be using C++ because that's just faster for this, for my purposes. So we're going to go here. 1 second. So we're going to go here, and what we're going to want to do is I've got everything set up here, as you can see. So I've got you want to make sure you have your include, your using namespace std, and you're using long. I just prefer to keep it that way. It makes more sense for me. And I have my int main with my IO kind of ready for me, and this is just making the IO a little bit faster. So now what we need to do is we need to start off by reading in the input. So we're going to have an int n. I'm sorry for the lag. My computer's a little bit laggy. We're going to have int n, and we're going to send into n. Ooh, that's very laggy. And so then what we want to do is we want to read in our string. So we're going to say string s is equal to, or rather string s, and then we're going to send into s. And then what we're going to do is we're going to, once we've read all of this in, we now need to kind of parse this. And so how do we parse this? Well, we're going to use something special, and this is going to populate our prefix array. So the first thing we need for that is our actual prefix array. And so what we'll do with our prefix array is we'll put in our prefix array, and then we'll set the first value. Because it's a prefix array, we can't kind of go back on the first value. So we have this kind of code, and this will just give us, we have a prefix array of size n, and we also have populated our first kind of, you would say, index. So next, what do we do? Well, next, what we're going to do is we're going to populate the rest of this prefix array. And the way we're going to kind of do that is we're going to just go through each kind of character of the string, check what type it is, and populate that array. And so that is going to look something like this. And we're just iterating for I equals 1 to n. We're going to populate the prefix array in the exact same way we did here. But then we're also going to prefix it by adding it to the previous. And that will kind of populate our prefix array. And so now what we need to do is we need to kind of get our suffix array ready. And the suffix array is going to act really similar to the prefix array. We're just going to have a suffix array of size n, and we're going to set the last index of the suffix array to the last index of the prefix array, again, because it's a suffix array. And again, from here, it's straightforward. What we're going to do is we're going to kind of get this for loop in here, and this for loop is going to populate our suffix array, except slight difference. Instead of adding like a prefix array or a suffix array would normally, we're actually finding the minimum. And that's why I've named it msuff, just to keep it clear that this is not a regular suffix array. This is a minimum suffix array. So this is getting the minimum value as a suffix array. And so now is where the interesting things start, because now we need to start actually going through each and everything and actually kind of calculating, going along and along and along, seeing what value are we hitting, what is our final count going to be, and checking if we're going to kind of hit that overflow point where, oh no, our minimum value is going to not work anymore. So here I am putting just two regular variables, and the first one is mprev, and mprev is going to give us the minimum previous value. Now, why do we need the minimum previous value? Because remember, we can't change any of the minimum previous values. We can't change anything that happened in the past with this sequence. So if at all that past minimum previous value is going to be less than 1, we can stop right there. No matter what we do for any of the following, you would say, no matter what we do for any of the following indexes, it's not going to change the fact that we've still got a -1 there. We still got a point where we've got a negative value, and that really breaks everything. So that's what that mprev is there for. It's just a quick little check to make sure we're not breaking behind us. And then the count is there for obvious reasons. That's going to be our final answer. So now we're ready to start building our for loop. And so the for loop is relatively simple. The first thing we're going to do is we're going to start off by iterating through each value of n. And then what we've got to do is we've got to put in that check to make sure that our mprev is actually not kind of exceeding what we want. And that statement is relatively simple. It's just as simple. If mprev is less than 0, break. That's all we're doing there, is we're just checking, is mprev less than 0? If so, we're done. We don't need to check anything else. Just return the count as it is. Now, on the chance that mprev is not less than 0, we need to see if we're actually, if the kind of position that we're flipping will change the values to 0, will accomplish what we want it to as per the problem, or not. And so the way we do that is with another if statement. And so that if statement is going to look something like this. You can implement it in different ways. I just kind of copy pasted the code from up here, and that's this code right here. It's the same for both of these. It's just checking if the msuff, which is what I said earlier, the minimum index, the minimum value, plus this right here, which is just giving us what it is. That's all it is. It's really giving us what the effects of flipping will be, is equal to 0, and that's checked in our first part, and the prefix plus this is equal to 0. And that's checking the second part, that at the end, when we apply this change, it gets to 0, and count plus plus. And the final thing we need to do in this one, I'm going to show you right here, is we're going to do mprev is equal to min of mprev, and what we need is the msuf, or rather, actually, what we need is the prev, we need the prev of I, and that's it. And so we've got our mprev. And now we're ready to finish this off, and the way we finish this off is by starting out, or however you want to say it, printing it out our answer. And printing out our answer is a relatively simple. And so we do exactly that. We sound out our answer, and we're done. That's actually all the problem is. So I'll open up a new terminal right here, and we've got this new terminal open right up for us, so we can get to work on compiling this. So we'll use a, sorry for all that CDs, we will use a G++ minus std equals C++ 11, because I'm going to be compiling this in 11. Warnings will turn on all, O2, and we'll say arbs.cpp, and O, and then arbs. And you can compile this in any in the language that you're using of your choice. And this is really language specific, but I'll just compile this. It should return with no errors, and we'll wait for it to kind of return at all. And in the meantime, oh, we have some problem. I have put prev even though I had meant pref, and that's right here. So there's one error. If you caught that, good job. I did not, obviously, because I wrote it. So we've put pref, and that's because it's a prefix and not a priv. And once this returns, we can get to work on /arbs, and we can copy our input. And our input, and I'm not showing this, but I'm actually copying it, and we get 3. Let's copy this next input. We get none. Let's copy this next input. 1 is 0, and if you're following along, you should be able to confirm these are all the right results that we are getting. Now, we can actually, I can go back here. So what we'll do is we'll submit this into not 17, we'll submit this into 11. I'll choose my file in Musico. And I store everything in Musico, that's just because it's where I store all my coding. I just renamed it like that. Videos, bracket sequence. Alright, here is the problem, and we will submit it. You're about to see a bunch of solutions that I've done for this, submissions rather. A lot, quite a bit. It's been submitted successfully. It is accepted in 46 seconds. Would you look at that? 46 seconds. Now, in fact, the only difference between this and this is the fact that in this one I compiled in 17, so we'll ignore that. In this one, I did not put the iOS, and in this one I did, and that just took it down by like a third. So just another quick reminder, always, always, always put your iOS and sin.type. This will speed up your code by a lot. So that is how you kind of would solve the E almost regular bracket sequence. If you did enjoy it, please don't forget to like and subscribe. I really do put a lot of effort into these videos, and I hope you guys enjoy them. And you guys liking and subscribing is the way that I know that. So please don't forget to like and subscribe. Leave a comment with the problem that you want me to do next, and I will catch you all in another video. Bye.